When Boston Dynamics showed Atlas hauling a 50-pound mini-fridge, you saw a robot lifting a heavy object. But the real story is not the lift itself. It is the invisible engineering shift required to make that movement stable. Most viewers see a marketing stunt. The reality is a fundamental transition from balancing a robot to managing force. By the end of this analysis, you will understand the specific torque-to-weight ratios and control loop changes that separate a lab demo from a machine ready for unstructured work. Let us look at what actually happens when a bipedal robot picks up a load like that. Under normal walking conditions, the control system operates in a balance-centric mode. The robot's center of mass stays tightly within its support polygon, the area defined by its feet on the ground. The primary goal is simply to stay upright. Linearized dynamics models work well here because the forces are predictable and the robot is light. But introduce a 50-pound fridge and the physics change instantly. That load shifts the robot's center of mass outside its support polygon. The machine is no longer just walking. It is fighting gravity with a counter-torque that its standard control loops were never designed to handle. This is where the first major engineering hurdle appears. To maintain stability with that heavy load, the robot must transition from a balance-centric regime to a force-centric regime. In this new mode, the control stack must generate massive counter-torque through the hip and ankle actuators. The linearized models that worked for empty-footed walking fail completely. The system now requires full non-linear model predictive control to calculate the correct forces in real time. The robot is no longer just following a trajectory. It is constantly solving for contact force distribution across 3 legs and the fridge's center of gravity simultaneously. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the mechanical requirements for this shift. Achieving this feat demands a torque-to-weight ratio increase of approximately 30 to 40% in the hip and ankle actuators compared to a baseline walking gait. That is not a small margin. It requires the actuators to operate near their saturation points. If the robot were designed only for walking, those joints would simply lock up or fail under the sudden load. The mechanical convergence is evident because the robot does not just lift the fridge and stop. It must walk while carrying it. This forces a shift from position control loops to impedance or force control loops. The system must absorb the impact shock of each step without toppling, acting like a spring that can tune its stiffness on the fly. Now consider the computational burden of this operation. The robot maintains a 100 Hz control loop while solving for the complex dynamics of the load. That is a massive amount of processing for an embedded controller. The latency limits of the hardware are pushed to the edge. You are asking the machine to replan its trajectory in real time because a pre-computed path is useless when the load shifts. This exposes the fragility of purely kinematic planners in unstructured environments. If the robot relies on a static map of where it thinks the floor is, it will fail the moment the fridge slides or the floor texture changes. This leads to the most critical failure mode in unstructured work, slip propagation. In a lab demo on flat ground, a slip in 1 foot might be corrected by a simple balance adjustment. But when carrying a 50-pound fridge, the weight distribution is uneven and dynamic. A slip in 1 foot instantly alters the torque requirements for the entire kinematic chain. The friction coefficient under the fridge changes the physics of the whole system. The robot must replan instantly, not because it hit an obstacle, but because the load itself has changed the ground reaction forces. This dynamic coupling means that every micro adjustment in the fridge's position ripples through the robot's joints. From a career perspective, this capability marks the industry pivot from simulation to reality gaps in locomotion to perception to action gaps in manipulation. For years, the bottleneck was getting robots to walk reliably. Now that locomotion is solved, the new bottleneck is sensor fusion. The robot must estimate the fridge's shifting inertia and friction coefficients in real time. It cannot just assume the load is static. It must perceive the weight, the center of gravity, and the friction of the floor as it moves. This is the difference between a robot that can lift a box in a simulation and one that can haul a fridge through a cluttered warehouse. The absence of hard engineering metrics on actuator saturation points in public documentation means we rely on the observed behavior to infer the underlying stress. The fact that the robot can maintain a 100 Hz loop while solving for contact forces suggests the embedded controller is operating at the very limit of its latency budget. Any delay in processing the sensor data could result in a loss of stability. The robot is essentially walking a tightrope where the rope is moving and the tension is changing every millisecond. This demonstration proves that the control software foundation for complex manipulation exists. The trajectory optimization and inverse kinematics required for dynamic movement are no longer theoretical. They are being applied to loads that push the mechanical limits of the hardware. The 30 to 40% increase in torque demand is the key metric that separates a toy from a tool. Without that mechanical convergence, the robot would simply tip over. With it, the robot can adapt to the unstructured environment. The transition from balancing a robot to managing force is the critical threshold for commercial viability. It requires actuators that can handle the extra load, controllers that can process the nonlinear dynamics, and sensors that can perceive the shifting load in real time. Until all three converge, robots will remain confined to structured environments. The mini fridge stunt is not just a flex, it is a benchmark for the future of robotic work. It shows that the gap between a lab demo and a functional worker is closing, but only because the underlying engineering has matured to handle the complexity of real-world physics. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.